Large power transformers are the key building blocks that allow us to transmit AC power from generation stations to the loads in our homes and facilities. Although the principles of operation are the same as when they were invented in the early days of electricity, the design and construction of transformers has been continually optimized to make them more capable and safer to operate. In this video, we will discuss construction, loading, protection, safety, codes and standards, operation and maintenance, and accessories for today's modern power transformers. Let's get started. The central function of a transformer is to convert the input or primary voltage to a desired output or secondary voltage, generally determined by the needs of the connected equipment. This voltage transformation is accomplished by means of the magnetic induction, where the magnetic field shared between windings is equal, but the voltage induced is proportional to the number of turns in the coil. The core and coil assembly has an inherent impedance, which acts as a throttle for the energy flowing through the transformer. A unit with higher impedance will limit the short circuit current the coils will experience, but will impact the transformer losses and system power factor. For standard distribution transformers, the IEEE have established standard impedance tables for transformers of a given kVA. The function of the transformer core is to create a focused path for the magnetic flux or field created by the transformer coils. This shared flux path tightly couples the transformer coils together, playing a crucial role in the efficiency and performance of the transformer apparatus. Transformer cores come in several shapes and sizes, but can broadly be categorized into two groups: stacked core and wound core. Stacked cores most often feature three legs and are made of silicon steel laminations. These are typically used on larger transformer designs that feature at least one delta connection. Wound cores are fabricated from a continuous strip of wound core steel. The strip is split into many individual layers which are wrapped concentrically to create the transformer core. Most often, in a 5-legged configuration, the wound core can be used for YY and grounded YY configurations. The core material can either be grain-oriented silicon steel or amorphous steel. Different core types, sizes, materials, and grades can all affect the operating losses of the transformer in the form of core loss. Core losses, also called no-load losses, occur continuously while the transformer is energized and can contribute significantly to the total cost of ownership. Most medium voltage distribution transformers consist of two windings, the primary and secondary windings. The primary winding is connected to medium voltage, typically 5 to 35 kV. And the secondary winding is connected to the load, which can be a variety of devices from large machinery to lighting and residential devices, generally below 5 kV. The primary and secondary windings are layered concentrically to fit the core. Thermally upgraded paper, or in some cases resin, acts as both a mechanical and dielectric barrier for the raw conductor of the windings. The winding material can be copper or aluminum, with aluminum typically being less expensive and offering similar performance on an optimized design. Once the windings are on the core coil assembly is complete. For dry-type transformers, the construction is nearly finished. The core coil assembly must be installed in a ventilated enclosure and the appropriate terminations added. Liquid-filled transformers utilize dielectric fluid both to remove heat from the coils through convection and to reduce the clearances between live parts. Modern liquid-filled distribution transformers are filled with biodegradable natural ester fluid like FR3. FR3 and other high fire point fluids also meet code requirements dictated by organizations like FM Global and Underwriters Laboratories, or UL. The resistance to fire drastically increases the safety of the liquid-filled transformer designs, allowing users to take advantage of the performance benefits of a liquid-filled transformer for indoor and outdoor applications. The liquid-filled transformer is sealed in a steel enclosure with primary and secondary terminations brought out of the tank through appropriately rated bushings. Depending on application, the transformer may also feature lockable enclosures to safeguard the terminals, as well as various gauges, sensors, or controllers mounted on its exterior. Common three-phase transformers have a kVA ranging from 15 all the way up to 12,000 kVA, with primary voltages going up to 46 kV and basic insulation levels, or BIL, to 250 kV. Medium voltage distribution transformers are engineered to order and are often based on customer specification. Customers may specify precise performance ratings and features for a transformer, but at a minimum, all Eaton transformers are built to applicable IEEE standards. The BIL is an important design criteria for transformers and should be considered to optimize the lifetime for a given application. Although a typical transformer has no moving parts that may wear out over time, a transformer will age and become increasingly susceptible to failure due to dielectric breakdown. The insulation paper used in the coils of a transformer, along with the fluid in the tank, are the two main materials that provide the dielectric strength between the live parts of the core coil assembly and ground. As the insulation paper is subjected to heat, moisture, and oxygen, it deteriorates, becoming more brittle over time. This deterioration is one of the main causes of transformer failures. Modern production processes minimize the exposure to moisture and oxygen by controlling the manufacturing environment and drying the insulation in a vacuum chamber prior to submersing it in the dielectric. Removing the moisture as a variable leaves the heat generated by the transformer loading as the prime impactor to transformer health and lifetime. All liquid-filled transformers will contain basic ratings that they are designed to operate at or within, including kVA rating, voltages, and temperature rise values. It is critical the transformer is operated within its design parameters to avoid excess loss of life to the transformer. IEEE has distribution and power transformer loading guides for both liquid-filled and dry-type transformers that state that a unit operated at 100% load, 24/7, at 30 degrees C ambient temperature will last 180,000 hours or 20.55 years. Transformer temperature ratings are specified as the degrees C above a standard ambient temperature of 30 degrees C. Liquid-filled transformers are suitable for use up to 55 or 65 degrees C average winding rise. When designed with a high fire point fluid, the transformer can achieve 75 degrees C average winding rise. On days where the ambient temperature exceeds these design assumptions, the transformer is at risk to extra loss of life due to the excess temperatures exposed to the insulation. The transformer may also be specified with a dual rating at 55-65, 65-75, or 55-75 degrees C rise, in which case the transformer has an additional self-cooled overload capability. For example, at 100% load, a transformer will have a 55 degrees C rise, and at 112% load, it will be a 65 degrees C rise. The loading practices which you employ have a strong effect on the overall lifespan of the transformer. Understanding the consequences of a transformer overload allows users to size their transformers accordingly and recognize whether a loading practice is promoting efficient use of the resources or is leading to premature failure of the transformer. There are many types of transformer protection available that protect the transformer itself as well as maintain the safety of nearby people and property. These devices can be tailored to a specific transformer arrangement and are often required by code. When coordinated with upstream and downstream protection, these devices can provide protection against a full range of events. The two main categories of protection types include overcurrent protection and overvoltage protection. Overcurrent protection devices include fuses, breakers, and interrupters, with fuses being the most common type for transformers. If fault current or heavy overload current flows on the system, the metal conductor inside the fuse is designed to melt and open before the equipment is damaged. Oftentimes, a transformer will be equipped with an expulsion fuse in series with a current limiting fuse or isolation link. The expulsion fuse will protect the transformer from secondary overcurrent events, while the current limiting fuse will protect nearby people and system equipment by limiting the energy during a high fault current event. If the expulsion fuse is a bayonet-style fuse, then it can be easily replaced from the outside of the transformer tank after the fault condition is repaired. A type of breaker that is unique to Eaton transformers is the vacuum fault interrupter, or VFI. This device is integrated directly into the transformer as an electronically tripped and resettable primary protection device. In addition to the protection, this device can also be used as a load break switch or on-off switch, and has electronic controls to allow for external control schemes. The most common type of overvoltage protection for a transformer is an arrestor. Arrestors protect from overvoltage events such as lightning, switching surges, and ferroresonance by reducing the surge voltage seen by the equipment. There are 4 basic arrestor classifications recognized by ANSI, which include station, intermediate, distribution, and secondary arrestor classes. Arrestors are defined by a duty cycle rating and a maximum continuous operating voltage, or MCOV. The duty cycle rating indicates the ability of an arrestor to withstand repeated voltage surges on the system. The MCOV rating is the maximum voltage that may be applied continuously to the arrestor. Arrestors can be located external to the transformer tank in live front or dead front styles, or in the transformer tank under oil. Medium voltage distribution transformers deliver a significant amount of power from the grid connection to the secondary with high amps on the low voltage side. This extreme amount of power is throttled only by the electrical impedance of the transformer during a fault condition. However, it is still more than enough to devastate equipment or personnel if an arc flash event were to occur. Arc flash events may occur during early commissioning or after years of use, but are often due to lack of maintenance or operators not following safety protocol. Risk reduction involves reducing the likelihood of an arc flash event occurring. This would include incorporating features like, number 1, gauges mounted on the outside of the transformer, 2, external fluid sampling ports, 3, externally mounted nameplates that you can see without opening the enclosure, 4, externally accessible on-off or load break switch to ensure the transformer is de-energized before access, 5, a 4-position loop switch mounted externally for sectionalizing control, or 6, even adding smart sensors and controls so you can remotely monitor your transformer. The commonality in these designs is they create a way to access key maintenance or operation devices within the transformer without entering the main enclosure and arc flash hazard zone, thereby limiting the risk of the arc flash events occurring. Energy reduction, on the other hand, involves lowering the incident energy by reducing the available fault current or the clearing time if a fault were to occur. This can be done by raising the impedance, lowering the kVA, or via more sophisticated methods. For example, fast reacting protective relaying or arc light detection can de-energize the transformer quickly in the event of a fault. In any event, all arc flash energy reduction methods aim to lower the incident energy at the transformer output, typically the low voltage terminals. Oftentimes, transformers contain primary fusing or are fed by a primary vacuum interrupter. However, these devices can be slow reacting to the secondary arcing faults, and in some cases take several seconds to fully clear due to the required inrush coordination. In most cases, the incident energy in the zone from the transformer secondary terminals to the LV main breaker is very high, and special care should be given. Employing incident energy reduction methods as suggested previously will help protect your equipment and personnel. Codes and standards govern the construction and installation of electrical equipment. There are 2 critical reasons why the codes and standards are so important for all types of transformers. First, there are organizations such as IEEE or NEMA to create the standards and help ensure the equipment and systems are designed and built consistently. And secondly, which is equally if not more important, is the aspect of safety in the transformer and system design guided by codes like the NEC. As it pertains to construction and design, the main aspects of the transformer are dictated by ANSI IEEE standards. Things such as phase conductor clearances, voltage withstand, bushing arrangement, coil insulation level, average temperature rise, external cabinetry, etc. are all dictated by IEEE requirements and therefore ensure a more consistent and safer arrangement in the field. These are the primary standards used for liquid-filled and dry-type medium voltage distribution transformers. There are many other standards that may be applicable to more specific applications such as solar PV systems or network vault type applications. While IEEE dictates the construction layout requirements, it is the National Electrical Code, or NEC, that is responsible for installation rules. The NEC splits medium voltage distribution transformers into 3 main categories: mineral oil filled transformers, less flammable liquid filled transformers, and dry type transformers. Mineral oil transformers may be installed outdoors or indoors, but only in vaults when installed indoors. High fire point fluid insulated transformers may be installed indoors or outdoors without restrictions. Dry transformers may be installed without restrictions. The primary focus of the NEC is to ensure proper and practical electrical interconnections are constructed, chances of electrical fires are minimized, and the safety of the operator is optimized. For each type of transformer in given location, indoors or outdoors, there is a specific NEC article to which you can reference for your guidance. 3-phase pad-mounted and substation transformers can be equipped with a variety of optional equipment. Most such accessories are factory installed and no field work is required to prepare them for operation. A liquid level indicator is provided to aid in the systematic inspection of the transformer under load. It consists of a float arm inside the tank, an indicating pointer, and a magnetic coupling between the two across a liquid-tight separation. Under normal operating conditions, the pointer should be between the low min and high max level markings. The temperature gauge is furnished to indicate the top liquid temperature in the tank in degrees centigrade. The temperature-sensitive element is mounted in a leak-proof well, permitting removal of the thermometer without lowering the oil level. The device is furnished with an additional red pointer to show the highest temperature attained since the last reset. To reset the maximum indicator, turn the knob in the center of the dial. The pressure vacuum gauge indicates whether the gas space in the tank is under positive or negative pressure. The pressure will vary depending on the transformer temperature. If the transformer is de-energized or operating under light load and low ambient temperatures, the pressure may be negative. If the indicator reads 0 and does not change under any loading conditions, the transformer should be checked for a possible leak in the seal. Transformers may be furnished with a winding temperature gauge. A temperature-sensitive probe is mounted in a leak-proof well, permitting removal of both the instrument and probe without lowering the liquid level. The well is heated by both the surrounding liquid and a heater element, which is energized from a current transformer mounted inside the tank to simulate the hot spot winding temperature gradient. The combination of the two temperatures is indicated on the gauge. An additional red pointer is furnished to show the highest temperature attained since the last reset. In order to increase the transformer load without overheating the windings, the set of fans can be furnished as an optional item. Fan control consists of a contact on either the liquid temperature gauge or the winding temperature gauge, along with a manual auto control switch. For continuous operation, the switch is turned to the manual position. In the auto position, the fans are controlled by the contacts on the temperature gauge. For contact and temperature settings, refer to the schematic furnished with the transformer. The tap changer provides a means of changing the voltage ratio of a de-energized transformer without breaking the transformer seal. It is operated by means of a rotatable handle located on the side of the transformer. The tap changer is normally provided with 5 positions, as indicated on the tap changer dial plate and transformer instruction nameplate. This allows for a 2.5% or 5% increase or decrease in the voltage. Eaton's VFI transformers utilize vacuum interrupters to provide fault current interruption and load make or break switching capabilities. The VFI transformer uses the same technology in Eaton's VFI pad-mounted switchgear. VFI transformers can be specified for either transformer protection or loop protection. When the VFI is on the coil path, it can protect the transformer and low voltage in overcurrent situations. When the VFI is on the loop path, it can protect the loop or downstream section of a feeder. Consequently, on a loop, when a downstream fault occurs, the VFI breaker trips, isolates the fault, leaving the transformer load uninterrupted. In specialty applications, 2 VFIs can be used in one transformer to protect both the VFI coil path and the loop path. The VFI mechanism in a VFI transformer has a hot stick operable handle located on the faceplate of the transformer, with operating mechanisms configured for ganged 3-phase operation. The VFI mechanism is opened by pulling down the operation handle into the open position. The VFI mechanism is closed by briskly pushing up the handle into the closed position. If the VFI mechanism has tripped as a result of a fault or overload condition, the mechanism must be reset before it can be closed. To reset the mechanism, firmly pull down the operation handle down towards the ground until the latch resets. After the latch has been successfully reset, the VFI interrupter mechanism can be closed normally. Finally, a visible disconnect is an option that is often installed with a VFI, where the VFI opens the power path and the disconnect provides visible isolation. When installed without a VFI, a visible break opens the power path and provides visual isolation. Transformers, like all power distribution equipment, must be properly installed and maintained by competent personnel who have been trained and understand proper safety procedures. Eaton transformers are designed and manufactured to spend their lifetime outdoors. Oftentimes, a transformer is received before the site is ready for installation. Prior to installation, transformers may require temporary storage. Whenever possible, the transformer should be stored at its permanent location. Here is a limited list of recommendations for units in long-term storage to help ensure that they are ready for service once needed. Close and seal the terminal compartment doors to prevent damage to bushings or other attachments. Coat exposed bushings with electrical grease to prevent oxidation on the surface of the bushings. If there is a heater inside the control box, run it continuously to eliminate internal moisture. Apply a nitrogen blanket to raise the pressure to 2 to 3 psi. On a monthly basis, visually inspect the transformer for leaks, including a visual check of all gauges. If a unit is rated for indoors, containment pans should not be installed if it is temporarily stored outdoors. If the unit is rated for indoors and has exposed electronics, the devices must be removed or properly covered. A transformer should be located on a level concrete pad of sufficient strength to support the weight of the unit. The location of the transformer, whether indoor or outdoor, should provide for adequate accessibility, ventilation, and ease of inspection. Generally speaking, the transformer should be at least 24 inches from any obstruction. New transformers or transformers which are being energized after a period of storage should be thoroughly inspected before connecting them to the power distribution system. At a minimum, inspections should include the following. Number 1, the transformer exterior should be inspected for nicks, dents, and scratches. Number 2, inspect and repair leaking or improperly tightened gaskets and seals before the transformer is placed in service. This could include tank cover, manhole or handhole, bushings, fuses, switches, etc. Number 3, the transformer leaves the factory with a slight positive pressure. However, due to the changes in atmospheric conditions, the unit may arrive under vacuum or negative pressure. This itself is not a cause for concern. However, continued absence of either negative or positive pressure may indicate a leak in a gasket seal or a tank seam and require further investigation. Number 4, the liquid level inside the tank must be checked. On transformers equipped with a liquid level gauge, the liquid level may be read directly from the gauge. At 25 degrees C liquid temperature, the liquid level gauge should point horizontal. Number 5, oftentimes startup or commissioning testing will be required by code prior to energizing the transformer. The local electrical authority will determine the final requirements. However, this will often include basic needed testing such as transformer turns ratio, winding resistance, insulation resistance, or Megger testing, as well as a baseline dissolved gas analysis or DGA test. Once the transformer has been thoroughly inspected and tested, the primary and secondary terminations can be connected. Connections must be made without placing undue stress on the bushing terminals. Conductors should be securely fastened, torqued appropriately, and supported properly, with allowance for expansion and contraction. The ever-improving design and operation of power transformers have added new capabilities to help you create a more safe, reliable, and flexible power system. If you'd like to see transformers in action and learn more about transformer options for your power system, contact us or your local Eaton representative to visit one of Eaton's Power Systems Experience Centers today.